LLMs use then I just range through my
All right,
data.
let's get started. So today we are going to shift our topic of discussion from post-training and reinforcement learning to evaluating language models. So in this class, we will kind of go through an overview of different ways to set up language model evaluations and kind of look at how things have evolved historically as the capabilities of LLMs have increased over the past few years. And then kind of where we're going is once we discuss these kind of paradigms of benchmarking, we'll start talking about more complex evaluations and also systems built using language models as like modules. And so these are more in line with agent-based systems that we see today. All right, so our topic for the day is benchmarking. So how do we figure out how good an LLM is at various different tasks? So now we've completed pre-training, we've completed post-training, and we might have deployed our model to a wide population of users who all have many different needs, and we want to basically try and figure out if the model is handling all those needs appropriately. So first, let's start with the kind of definition of what goes into a benchmark. So a benchmark generally consists of, I would say, roughly three things. So one is data. And in the most kind of common case of a benchmark, this data is static. And so this means we have a fixed set of prompts, right? So it could be x1, x2. And so the idea is that whenever a new model comes out, we will generate responses from the model for each of these prompts, and we will evaluate them using some metric. This is in contrast to kind of newer benchmarks, which are dynamic. And so here, the benchmarks are evolving and have kind of updated inputs. And so the probably the most prominent example of this is the chatbot arena or LM arena, which we'll see later on in the class, where models are kind of ranked by user preferences on data that users of the website are putting into the models. And so here we see different kinds of measures of how good a model is based on, in principle, how often would a response by model X be preferred over response by model Y. Okay, so this is one kind of distinction in benchmarks that we'll see, static versus dynamic. There's also differences in the task distribution. So before LLMs became so good, here, let me use my color coding. Before LLMs became so good at many different tasks, we would generally pick one task, build a benchmark for it by collecting data for that one particular task. We would have a metric that was very specialized to that task, and then we would rank all the models on our test set. So this is how NLP developed until the release of GPT-3 and general like kind of multitask models that followed after that. The single task benchmark is still very common today, but it gives you only a very narrow view of what the model is capable of. So some prominent examples are translation, summarization, and things like this. So these tasks the NLP community had been working on for decades prior to the advent of LLMs, and they're very well established data sets and metrics for these tasks. So this is in contrast to what I'll call broad task distribution. And this is kind of similar to what we saw with instruction following data sets, where the idea is to collect a data set of as many different tasks as possible with instructions on how to complete that task and reference outputs. And so here, this is more in line with evaluations of like general purpose chatbots like ChatGPT, where you want to measure the model's capability on as diverse of a collection of tasks as possible. For instance, this could be assess how well the model does on a random sample of user prompts to ChatGPT. And so some benchmarks actually look like this, where they take just a diverse sample of real user prompts and kind of try and rank models on how good their responses are. So, wide range of focuses in terms of task distribution as well. These are basically like two ends of a spectrum. In all cases, though, you need some data, some prompts to put into your model, and you generate some responses. So the second thing you need when making a benchmark is a metric. So this is very important. You need some way to measure the performance of the responses that your model generated, the performance or quality. So, if we're given a prompt X, given an X, our model produces Y, how good is Y? Right, so in the machine translation case, as we'll see a little later, we might have a sentence and say translate this from German to English. Our model spits out a translation, and now we need to come up with a way to score how good that translation is. So in some cases with a metric, you'll have external information. So you might have, for example, a reference translation that a human has created, and you can measure the LLM's translation in comparison to that reference. In other cases, you may not have a high quality reference available, and so here you need to be a little more clever in how you come up with the process of judging the quality. So in general here, we are discussing automatic metrics, but as we will see later, as the automatic metric becomes more complicated and the task that you're judging becomes more open-ended and subjective, these automatic metrics need to be themselves evaluated, right? You don't know how much you should trust the score that's being spit out of some metric. You may need to benchmark it against human evaluations of quality. But for some of the tasks that we'll be considering, even humans are not good at performing an evaluation, right? Like the canonical example is, evaluate a short story generated by a model, right? It's easy to do if the short story is like completely incoherent, or it has grammar errors, or repetition or things like that. But if none of those is present in the response, it becomes a lot more subjective, right? Like you might want some notion of how enjoyable is the story to read, or how creative is it. And for those kinds of things, it's hard to come up with a schema that a human could follow to evaluate those properties and have high agreement with each other. So the metric design is a very, very important problem. A lot of big labs are putting a lot of money into this. You'll also note that this question here is exactly the one that we were trying to solve with the reward model, right? When we were talking about post-training. And so a natural question is, well, why don't we just use our reward model that we obtained through all this effort with all these human preference judgments and trying to mimic them? Why don't we just use our reward model to evaluate the responses in these various benchmarks? So what are some issues with this that you all can think about? I could just take an off-the-shelf reward model, use it to score responses from different models, and then rank them based on the score.
Aren't reward models like individualized for each model, but they're not like necessarily consistent across all the models? Right?
That's a good question. That's a good point. So like ideally the reward model is trained only on the responses produced by a single model, right? The like SFT model. However, in practice, reward models are trained on data from many different models and just as many preference judgments as you can get. So if you have a reward model like that, where you just have like millions of preference judgments and you've trained it from many different models, you've trained a model to kind of mimic those human preferences, you could conceivably get, get out of the issue that you mentioned. But yeah, that in principle is a big issue. What are some other ones?
The rewards are not that interpretable in terms of like how the quality of the responses were.
So the rewards are certainly not interpretable. That's a great point. They give you a score. You don't know why it gave you that score, right? All you know is that in general, this score compared to a worse response will correlate with a human preference. So that is one reason. It's not interpretable. The relative differences between models in terms of average reward model score, you don't really know what it means if like one model has an average reward of 2 and another one has an average reward of 2.5. Like, is that a big deal? Is that not? So that's a good point. Yeah.
You're not necessarily guaranteed that a high reward means high quality, like if you reward hacking.
Exactly. So we already talked about how reward models themselves are prone to reward hacking, right? Where you might want it to measure how good is this story, but actually it's measuring something like which story is longer, right? And so because it's so uninterpretable and subject to so many different things, it's really hard to say if it's actually like a high reward correlates to what you want to measure about the task. Okay, so great points. Those are the main reasons. I also wanted to just highlight a common kind of phrase that is discussed a lot when it comes to evaluation, which is called Goodhart's law. And this is just one sentence. When a measure becomes a target, it ceases to be a good measure. And so in the reward model scenario, we are using the reward model as a target, right? We are trying to maximize our expected reward. And so if we come back and then use the reward model to score the responses and rank them, we, as you said, leave ourselves open to all of these issues with reward hacking and divergence in human preferences and reward model scores and things like that. So generally, we want to have more kind of objective, high agreement type metrics that differ from the way that the model was trained, like using reward models. Okay. Finally, I just wanted to re-emphasize the distinction between human eval, which is high cost, both time and money. Oops. And also difficult for open-ended tasks. Not that automatic metrics are any better there. Versus automatic metrics, which are ideally fast and cheap, and for any task for which you want to use one of these, ideally correlates with human judgments. So these are important considerations. If you're trying out a new task, generally you want to do some human evaluation first, and then try and figure out what metric is best for your task by optimizing the agreement between your metric and the human data that you get. So because the development of these metrics is so difficult, we see a kind of clear breakdown in the types of tasks that people work on. So there's few people who are working on evaluation of story generation compared to thousands of people working on things like multiple choice exams, where it's very easy to evaluate, right? The model either gets the right answer or it doesn't. And there's no arguing about it. So the easier the evaluation, the more attractive it is to people building these evals. Okay, so before we get too much more into depth on different types of metrics, the last thing that most benchmarks are require is a protocol or setup for generation of responses. So this means everything from like decoding time hyperparameters. So some benchmarks will allow you to sample multiple responses and choose the best one. Multiple responses versus just one. And so this is quite common with especially coding benchmarks. You might see these terms like pass at k versus pass at 1, which refer to if you have like a coding task and your evaluation is does it pass a unit test or not. At pass at k, you allow the model to generate k different programs, and if any of them passes the unit test, it gets full credit. Whereas with pass at 1, the model generates just one sample and it gets no credit if it fails the unit test. So why might this pass at k be a useful measure for certain tasks? Yeah, I mean, I think like more broadly speaking, if you are in one of these setups where you're evaluating with a unit test, the idea is that unit test is quite easy for a human to write. And if you're able to write down, like, here are all of the test cases that any program that is written in response to my prompt should pass, you might not care how many times the model has to try in order to fulfill those conditions. Like, depending on your task, you might have enough budget to generate, hundreds of candidate programs and choose the one that works best. So it really, in some cases, like if you're just prompting ChatGPT, you're not going to want to wait for it to generate hundreds of responses, and you're not going to be interested in reading all of those 100 responses to figure out which one you like the best, right? So in those kinds of settings, you're really interested in the score of any single one example. But in a case that's more constrained, like you just want anything that passes all of these tests, and you're willing to be patient, you don't need to manually review any of the responses. Pass set K is also a viable measure because it is kind of reflective of real world usage in those applications. Okay. Other things to consider here, tool use is something that we will talk about in the next class and when we're talking about agents. So far we've just talked about language models as generating text, and they receive a prompt, they generate some text, and that's that. We do something with that text. But nowadays it's more complicated than that. Models can generate code that can be executed, that can interact with external APIs and actually take actions in the world, and they can be chained together, right? All of these actions can, depending on the result in another call to the LLM to do something else, and at the very end you get some response that is shown to the user. So tool use is another kind of condition of a benchmark, where some benchmarks may say no tools allowed, no access to Google search or Wikipedia or things like that. No access to coding, executable code that you can run. And other benchmarks may be like, you can use whatever you want, your system can interact with anything, it just has to pass these tests, and that's what we're rating. So we'll talk more about this later if it doesn't make sense now, if you're thinking, how can an LLM run a program or something. We'll discuss that more in the next few lectures. Let's see, what else do we have here? Oh yeah, so there's other things like what is the system prompt and the overall task prompt that you're using. So you might have seen, or yourself tried to add all of these things into your prompts to LLMs when you're using them. Like if you're doing translation, you could say something like, you are the best translator of this language that ever existed. Translate this sentence in a as faithful way as possible. And maybe that has inclusion of that actually improves your performance on some data set. So, as a benchmark designer, you may want to standardize the system prompt that all of your models are using. In general, you want as simple of instruction as possible, just so that model developers can't tune their systems to perform well on very specific system prompts. Now, another thing kind of tying on to what we talked about in the last class is the reasoning budget. So we know that for many tasks, the model's performance improves as it is allowed to produce more reasoning tokens. So, if it's not really fair to compare a model on, say, a math benchmark, a model that has a reasoning budget of 20,000 tokens compared to one that is not allowed to reason at all, right? So you might want to have some standards on how much your model is able to think. Okay, great. Does that make sense? These are kind of the high-level things to think about when you're looking at new benchmarks. Okay, hello to you too. Let's go back here. All right, so now let's start looking at some examples of specific kinds of tasks, metric combos. And I wanted to show first the most canonical example of a static benchmark with a simple metric, and we'll build from there. So specifically here, we'll talk about machine translation, which again is like actually the task that gave rise to LLMs. Like a lot of the development of ChatGPT is directly traced back to things that were created to improve machine translation. So the whole concept of attention was developed in 2014 or 2013 to improve recurrent neural network models' ability to translate sentences. The transformer was literally developed for machine translation. All of the benchmarks that they showed were on translation from like French to English, English to French, things like that. These technologies were all repurposed later on for language modeling, and then post-training was developed and so on. But machine translation has a very rich history in the research community. So it was a task that people worked on for decades before neural network models even became popular. And there's many large data sets and evaluation studies that have been done to kind of standardize the task and make progress, meaningful progress in the community. So just to be clear, here we're talking about generally sentence level translation. So your input in our example later, we'll look at a German sentence X, and an output could be an English translation Y. And if you're using an LLM to translate, you'll probably have a system prompt as well, like translate the following sentence into English or something like that. So the important thing that I want to talk about here is regarding the metric. So in machine translation, we generally assume access to a reference translation. We'll call it yref. This translation is written by a real human translator. And so most of the data sets for machine translation historically have come from sources where there's naturally translations being produced. So like European Parliament proceedings, right? They take place in one language and they're translated by human translators so that citizens of many different countries can understand them. And so this has been happening for years and forms a very good source of data for this field because they're all publicly available. Okay, so the metric that we will be talking about is called BLUE, and it's a very simple metric that is based on n-gram matching. And so it has a lot of advantages because of how simple it is, but it also has many disadvantages also because of how simple it is. So we will look at both of those. So at a high level, BLUE computes the geometric average of a quantity called n-gram precision, where n varies from 1, which is a unigram, to 4. And this n-gram precision is just a simple normalized count. So you count up the number of matching n-grams between y and yref. So yref here is our reference translation that a human has written, and you divide that by the count of n-grams in Y, which is our candidate translation that the model has produced. And so the specific formula for blue, and I'm, by the way, just going into detail on this metric because it's widely used for now many other tasks that are not machine translation. It can be a good diagnostic, especially where like exact match to a reference is important. But in many cases, it's used incorrectly where you would not actually expect the exact match to be a predictor of how good the model's output is. But we'll talk more about that. So the formula for blue is we're going to sum up the, n equals 1, the precision of different n-gram values. So here, this 1/4 indicates that I'm weighting the precision of each value of n, so unigram precision, bigram precision, trigram precision, and 4-gram precision. I'm weighting them all equally, like 25%, 25%, so on. Now, this is just the geometric average of this n-gram precision. Blue additionally has a final multiplication with something called the brevity penalty. And this is because we want to penalize translations that are too short. So if you have a very short translation that just happens to contain one of the phrases that is in the reference, you might get a very high n-gram precision. However, your translation's obviously bad, right? And so blue includes this brevity penalty, which is 1 if the length of the candidate is greater than the length of the reference. So if you've generated more words than there are in the reference, you're not going to have this issue where you're kind of gaming the metric. And it decays. If the length of the candidate is less than the length of the reference, this brevity penalty decays with the difference in the length. So yref minus y. It's not important to know exactly how this brevity penalty is implemented, just that basically your score goes down as your candidate translation is shorter than your reference translation. So let's take a look at a simple example to show you kind of the pros and cons of this metric. So let's say I have a German sentence. Das ist ein kleines Haus. So this means this is a small house. And my model spits out a translation. This is a little house. Let's say I have a reference translation from a human, which is this is a small house. Oops. So what we do in general is we first compute the n-gram precision for all values of n from 1 to 4. Here we will just compute blue 2 to save time. So we'll compute both the unigram and bigram precision and take the geometric average. So let's do the unigram precision. We know that the denominator here is the count of unigrams in our candidate. So this thing has 1, 2, 3, 4, 5 words. And the numerator is how many of the words in the candidate match the words in the reference. So this is a house. All 4 of those words match, and we have one mismatch between little and small. So our unigram precision is 80%, pretty good. Our bigram precision now we're going to look at the bigrams. That is a match, also matches our reference. A little does not match, and neither does little house. So we have 4 total bigrams in our candidate, only 2 of them match. And so now our brevity penalty here is 1 because these 2 things have equal length. So we can compute the blue 2, which is just the geometric average of these 2 precisions. And if you follow that formula, you get something like 63%, which is pretty good. In general, if you ask another human translator to translate this sentence, they may not get an exact match to the translation either, right? They may also say this is a little house or something else. So like your upper bound here is not 100%, right? That would mean every single time your LLM spits out an identical translation to the reference, which is just not feasible or attainable. However, in general, you want a higher score, right? So a system that achieves a higher score is probably doing a better job of translation than a system with a lower score. Yeah.
So for the brevity penalty, if the so it will take off like 1 if what's it called or it will, I guess, multiply it by 1.
Yeah, so it has no effect if,
So-
yeah.
Yeah, it has no effect if the length of the output is shorter than.
If the length of the output is longer than the reference, it has no
The
effect.
length of the.
So you can imagine here, if the candidate was just small house and we didn't have a brevity penalty, we would get 100%.
I see, okay.
So this is the reason. There are other reasons, like you might think, well, why don't I just compute the recall of the n-grams and do an F1 instead of doing this? But the recall is a lot harder to deal with in the case where you have multiple reference translations, which is kind of common in machine translation. But we won't talk about that here. We'll just assume 1 reference. Yeah.
Was there a specific reason that you choose to go to 2 gram, like 5 gram, or just?
Here, just because I didn't want to bother writing out all the other ones, but yeah, it's the same principle. So what I did want to do is discuss some of the drawbacks of this method. So let's say I have another candidate, y2 equals this house is small. So here, if I compute unigram precision, my candidate translation has 4 words, and all 4 words occur in the reference, right? So my unigram precision is 100%, but let's look at bigram precision. So here, this house does not occur in the reference. House is does not occur in the reference, and is small does not occur in the reference. And so my bigram precision is 0%. My overall blue score is also 0, despite the fact that this is a decent translation, right? It has the same meaning as the reference, but because we have such a strict metric here, we get no credit for producing this reference. So you can see kind of the pros of this approach. It's very, very easy to compute the score, right? You just split the string into n-grams and do some matching, right? Similar to what we did in n-gram models. The drawbacks, though, are that it has no accounting for semantic similarity, right? Otherwise, it would be able to say that y2 is highly similar to the reference translation. So there's many variants of things like blue that have been proposed to add more semantic similarity into the metric, but we're not going to talk about any of those in this class. What we would like to kind of summarize or just highlight that blue. It has a counterpart metric rouge, which is used for summarization. It's basically the same thing, but is measuring recall rather than precision. These are all string matching based metrics against reference. And so they are weak but cheap metrics. So ideally, we want a strong and cheap metric, but it's really hard to obtain those. So now let's kind of transition from this case where we have a static data set with a single task. I should have added that up here for single task. Now let's move to a static data set, simple metric, multitask with a broad distribution here. So probably the best example of these are multiple choice kind of exams. And generally these are multiple choice. Probably the best example of this is a data set called MMLU, which has a wide task distribution with 57 different subjects. So it's got like math, economics, biology, things like that, and it's got multiple choice questions for each of them. So I wanted to kind of just show some examples from these data sets, just to give an idea of how they kind of handle this wide task distribution. So let me switch over to the browser here. Okay, so this is the MMLU paper. MMLU stands for Massive Multitask Language Understanding. This paper came out in pre-ChatGPT times in 2020, but it has been and is still being used today, even though it's kind of reached saturation, and most LLMs are kind of exceeding the performance of they've saturated the benchmark. But let's look at some examples from this. So here is an example from the microeconomics subject. One of the reasons that the government discourages and regulates monopolies is that, so this is our prompt here, paired with all of the different candidates, producer surplus is lost, blah, blah, blah. And the correct answer is D here. So they have experts kind of write these questions. There are advanced versions of this data set where they actually took a bunch of college textbooks that had multiple choice questions in them, like at the end of each chapter, and they turned those into a data set to evaluate different models. You can actually do a lot within this multiple choice setup, right? So here, you can test conceptual knowledge of physics. You can use multiple choice to test mathematical reasoning as well. And so you can see that here. And here you have even like medical kind of questions that are being tested. So this paper was released, and for many years, most LLMs that were released had to report their MMLU score. It was like the basic benchmark that everyone wanted to see. I also want to just quickly show this benchmark, which is kind of an upgraded version where they write these questions. They have experts, domain experts, write questions, and they have other people go and try and answer the questions with full access to Google. They give them 30 minutes or an hour to try and figure out the answer to this question by searching as much as they could. And they take the subset of questions which the people trying to answer them failed to answer correctly. So they call it graduate level Google proof QA benchmark. We'll get to this later, but I wanted to show some examples here. So methylcyclopentadiene was allowed to react with this thing and this thing. A bright yellow cross-conjugated thing formed. How many chemically distinct isomers make up the final product? So it's still a multiple choice data set. They collected, not only the correct answer, but also an explanation of why, just to, I guess, help people understand what kind of reasoning was required. And then they had this expert validation here. The expert would answer the question and provide an explanation. And then once they see the correct answer, they would give some feedback on why they think they were unable to answer it correctly. This is still a benchmark that is being reported in new model releases today, although it also is getting to the point where it's saturated. This is also a data set where, people start discussing things like superhuman performance, where any single human is unlikely to be able to get a good performance on this benchmark because it requires expert knowledge in so many different domains. But we are requiring, or asking the LLM to exhibit this level of knowledge mastery. The very interesting thing about this benchmark, I'm not sure if it's in this paper, but it was released in, November 2023, and the presentation of this paper happened at a conference, I think that summer of 2024, so it had been out for a few months. And the presenter was like, look, we did all this work, but we have to admit that since we released our benchmark, models have already exceeded the kind of human performance upper bound of it. And so the benchmark had already been basically solved in a few months since its release, because things like GPT-4 had come out that were really good at these tasks. That also brings me to another important concept that I wanted to discuss, which is data contamination. So this paper has this kind of box that says, we request you do not reveal examples from this data set in plain text or images online to reduce the risk of leakage into foundation model training corpora. We incorporate this canary string into the data set to make it easier for training corpora to filter out our benchmark. So what they are trying to do is prevent model developers like OpenAI or Google or Anthropic from simply just taking their data set and adding it to their instruction tuning data set, their SFT data set, where that would be kind of cheating, right? Because if you train on this data set, the model could get a really high score on it without actually knowing anything about those topics. Unfortunately, this happens all the time. We have no transparency into the closed models, and the developers of those models have every incentive to train on as many benchmarks as they can, just to juice up their numbers and say that they're better than these other models. There was a very interesting analysis that was done recently where some lab took a collection of the most popular benchmarks and created new test examples with the same format as those existing benchmarks. And they re-evaluated all these models that have saturated the performance in the benchmark on the new test examples. And they found that there were huge differences in some models. Like model might get 90% on the public benchmark and get like 30% on the test set that the authors created with the like same task distribution, same difficulty. So this is an instance of data contamination where your benchmark is no longer measuring actual progress. It's just measuring how well the model memorized the test data set. And we will have a lecture on memorization versus generalization later on in the semester to kind of explain how this can happen and in what stages of training does this happen as well. But yeah, that's kind of what I wanted to talk about regarding these multiple choice exams. Like you can test a large variety of knowledge, you can make very, very hard questions, but in the end, it's still kind of limiting, right? Because you're really just testing in terms of what the model is generating. It's simply producing one letter, right? A, B, C, or D. Whereas most real-world usage of LLMs is not like answering multiple choice questions, right? It's actual generation of some longer form response. And so it becomes more critical to evaluate those. So let me just switch back to the iPad for a second to write down some summaries of what we discussed, and then we will move on to kind of the next class of evaluations that we're talking about. So here mentioned this issue of data contamination, where LLM is trained on the benchmark, so scores are inflated. Okay, so to avoid data contamination, it's very difficult if you have a static data set, right? Because if you release your inputs, and in the case of these exams, the correct answers, it makes it easy for anyone to evaluate their model's outputs quickly, but it also makes it easy for them to just train on that data set. So there are ways to mitigate this. For example, you could just release the prompts without the answer, and maybe they have to submit their answers to some centralized place that judges the correctness. But even that is not great, right? Because if you do that, someone could just reverse engineer the answers and train their model on them. And these companies have a huge amount of resources to do things like that. So really, like, the solution to this contamination problem is dynamic or interactive benchmarks where you don't have a static, like, here are the 400 exam questions. The prompts are changing every time. And so the most common or popular instance of this is the chatbot arena, which was, I guess, renamed to LM Arena recently. And so before we go into some examples, I just wanted to draw kind of a plot that shows the different kinds of evals and what they're intended to measure. So I think it's useful to think about benchmarking in terms of two dimensions. So one is kind of the task complexity and open-endedness, where something like a multiple choice exam, even if the problems are complicated, the output is very easy to evaluate, right? It's not open-ended. You have one of 4 choices that you can produce. Whereas on the right side of this plot, you might have something like story generation, where it's much less clear. There's many possible responses. And then on the y-axis, we can look at like how automatable, is that even a word? Automatability. So like, can I create an automatic evaluation for this task? So up here is the corner of like very automatic, very easy to evaluate tasks that are also not open-ended. So I would say something like MMLU is in this, or GPQA, which is the one we just looked at. You could also say machine translation is in this quadrant because although blue is flawed, it does correlate with human preferences on translations, and it's very easy to compute. And also the task itself is relatively constrained, right? Like translating a sentence is very different from writing a story. There's only a few like valid translations of any given sentence. That said, I would put it more to the right of these multiple choice exams. So over here we have like static, easy to evaluate benchmarks. Now the middle is something we haven't talked about yet, which consists of more long-form writing responses. So here we have things like MT bench and EQ bench, which we will look at in a second. So these tasks generally have a prompt that requires maybe a couple paragraphs in response. And there's no reference output or no easy way to judge the quality of these responses. So these kinds of tasks are generally also static, but hard to eval. And we automatically eval them using what's called an LLM judge. And so this takes many different forms, has its own flaws, but seems to correlate, at least on some tasks, with human preferences. And then like down here, we can put the chatbot arena. It's a dynamic eval. And you're not even evaluating automatically, but with human preferences. So this is kind of like a real-time evaluation of LLMs based on human preferences, not automatic evaluation. There's also many other tasks that are closer to this end of the spectrum that deal with agent evals. So we will talk about those later on. But generally, as the task gets more and more complex, it's more and more difficult to come up with automatic evaluations for those tasks. So let's kind of take a look at these now. And let's look at some examples from real benchmarks. Okay, so we've done this one. Oh, this was another example of a static evaluation benchmark. So this is from the human eval benchmark released by OpenAI, where you get like a specification of a program, like a Python function that you need to write, and the model is trying to generate the response. Generally, it's a pretty simple program, and it's very easy to check if it works with just tests, right? This is another benchmark that has been heavily contaminated now. A lot of models are trained on this task, so it's not very useful. Okay, so let's take a look at this EQ benchmark, because this is kind of a different benchmarking paradigm. So here, they have different categories, but we can look at, for example, creative writing. So here they have a ranking of different models. And you can see that there's something called a rubric score that is used to rank them. So let's look at how they're actually doing this. If we look at some sample outputs, we can get a sense of the nature of the task. So here's one of the prompts in this data set. The prompt says, classic sci-fi gives an example of an author to imitate, gives a title of the story that the model should generate, and a plot summary. Colonial Mars is being mined by corporations who take leases on indentured laborers, blah, blah, blah. It has a very detailed plot that the model should follow, as well as a length constraint. So your story should be 1,000 words. And so this is one of the model outputs. I think this one is generated from GPT 5.1, which just came out last week. And so it generates something, it looks like more than 1,000 words, but, and now we see the evaluation, which is from an LLM judge. So we'll take a look at how this is actually implemented, but the idea is that this will give you a score, but it gives you like a detailed analysis of why it came up with that score. So first you have this analysis. This piece demonstrates strong adherence to the prompt's requirements, blah, blah, blah. The characterization is effective. The dialogue carries the narrative effectively. Keep in mind that this is all generated by another LLM that's being used as a judge. We have no idea if we would agree with any of these things unless we actually read the story. And it is painful to read these LLM stories. They're really boring and have a lot of slop and just hurts your head to look through them, which, you know, it makes sense why someone would want to automate this. Okay, so here at the end we have the scores, right? So for all of these different categories, the LLM is asked to grade the story from a minimum of 0 to a max of 20, I think. And so here it was pretty good at adhering to instructions, maybe not so emotionally complex. Yeah, I mean, I don't know. I guess it gets a score for each of these, and then somehow that score is aggregated to get a single rating of the story. This is then done for many different stories, and all of the scores are averaged together. This benchmark notes that, you know, the judge model may not be deterministic. We may be sampling from the judge and might have different analyses every time. So they run it through the same judge, like every story, through 3 different iterations. So they sampled 3 different judgments for each story. And you can see the average score is fairly consistent here. So that says that in general, the LLM, whatever judgment it gives, it will give consistently. It does not mean that those judgments are correct in any way. And actually, this benchmark does not have validation with human judgments of these stories. So we're just kind of trusting that this is working. Or not trusting, like who knows. But there's also other things in this benchmark, like a slop category, which tells you what are the most repetitive words in the stories generated by this model. So this one really likes this phrase, chipped black nail. It used it 5 times in the 20 stories, black nail polish. You know, close enough now that he can smell. I guess this only occurred 1 time. Yeah, so there's some like, you know, other kinds of analyses that you can do when your output is now like a long form piece of text rather than a multiple choice answer. Okay, let's see what else I wanted to show here. So we'll talk more about LLM judges next. Yeah.
Which LLM is used for the judge?
Yeah, so they use the same LLM. I think it's the latest Claude model that's being used as the judge. But that's another problem with the benchmark, is that every time a new like state-of-the-art model is released, you might want to reevaluate everything you have using that as the judge. However, it's expensive to do that, first of all. Second of all, LLMs generally prefer stories that they generated over stories from other models. So you'll see like GPT-5 gives really high scores to stories generated by GPT-5 and lower scores to Gemini, whereas Gemini might really think that Gemini stories are better. So, you might want to use an ensemble of different judge models, but overall, this kind of area of evaluation is very sketchy. There's, we're evaluating things that we don't even know how to evaluate as humans, and we're just like giving it to LLMs because it's fast and easy to do that. And then we're like, oh, well, the LLM thinks that this model is best, so it must be best. But as we'll talk about more next time, this has led to a whole pushback against benchmarks because no one trusts the benchmarks. They might be contaminated, like people might have trained on them. They may be using LLM judges that no one can verify are actually doing the judgment properly. And even like people from frontier models who work on these models have been saying they don't use any of these metrics during the development of their models. They rely more on vibes, where they just like read a couple responses from the model and decide if it's better than the previous iteration. And so, people have tried to quantify what vibes are, of course, but this is really like one of the worst kind of, in terms of scientific rigor, fields right now is evaluation, because it's really not like a problem that people want to work on. They want to work on new models and stuff, but we've kind of run into a wall where the interesting tasks that you would want to improve your models are the same ones where it's not easy to do something like blue or multiple choice to figure out if they're good or not. Yeah.
So you said that, so since all of these benchmarks have like a ton of problems, what alternative are we using?
I mean, it's not a solved problem.
Okay.
So I think most researchers who work on tasks like these and people who are developing the models rely heavily on just reading the outputs of the model themselves,
okay.
and or like hiring humans to do the same thing. But yeah, it's really just not clear what the best way is to. Now, as we'll talk about in the next class, there are, you can do a lot of work on rubric design and validation and so on, but you can make these better, essentially, but you're still not going to solve the fundamental problems associated with them.
Okay, so I guess, I mean, we mentioned the multiple choice ones, like those won't really be good, like under any circumstance now, right?
I mean, you can keep making new multiple choice data sets. The thing is their shelf life is so limited.
They aren't complex enough.
Yeah, exactly. And they don't test any sort of generation behavior of the model. So this is an example from MT Bench, where here there's like a multiple choice question, but then there's a follow-up question that is more of a long form response. So give 3 examples of how the Fed buying bonds affects my daily life. And you have 2 responses, assistant A and assistant B. This benchmark uses GPT-4 to judge which response is better. So unlike an EQ bench where you would get a single score for one story, here it's a pairwise judgment. So you have 2 candidates and you have to say which one is better. And so here you see that it says assistant B's response is more helpful, relevant, and detailed. These LLM judges have all similar biases to reward models, like they prefer longer responses, they prefer responses generated by their own model family, blah, blah, blah. So it's hard to trust these things. Okay, I want to finally just show briefly some meta evaluations that are kind of analyses of multiple benchmarks. These are also very interesting, very different than what we've been talking about, but this is one by this Meter group where many of you might have seen this. It's more of a broad evaluation of AI capabilities. So the y-axis here is how long an average human would take to solve a task in one of these benchmarks. So like these math problems maybe take 4 minutes on average, whereas competitive coding or math problem or some of the ones in that Google Proof QA thing might take hours plus to solve. They're basically trying to show that as models have been improving over the years, the kind of task complexity in terms of how much time it would take a human to solve this task has been increasing. So models are getting increasingly good at solving complex tasks that are time consuming for humans. This thing was published in July 2025. And I think since then there have been more updates to this. This is another kind of one specific to software engineering. So this is the time horizon of software engineering tasks that different LLMs can complete 50% of the time. So you see like find fact on web is a very low effort task. Train a classifier, someone could do with under an hour. Fix bugs in small libraries, exploit a buffer overflow. So they're getting more and more complicated. You can see that GPT-3, GPT 3.5, 4, they were not capable of even the smallest time horizon tasks here. But as things improved, now like GPT-5 can exploit this buffer overflow and can do all of these other tasks. And so, it'd be interesting to correlate this with the number of job openings for software engineers. Probably you can see quite a stark correlation there. But like these are, meta evaluations of all of these different benchmarks that have been released. Okay, so next time we will talk a little bit more about LLM judges. And then we will start talking about agents, so chaining different models together with output from the environment. So I can take your questions offline after the class ends. See you all on Wednesday.